Hi everyone. Good evening to all. So in the last lecture, we were discussing Myhill-Nerode theorem. So the idea we have seen. Now today we will see the formal statement of Myhill-Nerode theorem. And also we have seen many non-regular languages. Proving a language is non-regular, that is very easy now. Yes or no? Okay. Are you finding that proving that a language is non-regular, that is quite easy? You can notice when a language is non-regular, when you have to keep track of unlimited number of possibility. Okay, so when you have to keep track of unlimited number of possibility, then in this situation language is non-regular. Okay, so this is the idea. So you can notice here so when you need to remember in one of the infinitely many different things, so this is important. Okay, this is how you can say a language is non-regular. A language is non-regular if you need to remember one of the infinitely many things. Okay, and what was the template? If you want to prove a language is non-regular, then what you will do? You will create a set. You will find. Okay. So what you will do? You will find infinitely many strings that need to be that cannot go to same state. Okay. You need to find infinitely many strings. Okay. Who cannot go to same state. Okay. None of them. Any two of them should not go to same state. Okay. So this is the idea. So this is the general pattern. Can you notice? Read this. Read this. So you can notice that find what you do, you find an infinite collection. Okay, find an infinite collection of strings. Find infinite collection of strings that cannot end in the same state. Okay, find infinite collection of strings that cannot end in same state. Okay, that cannot end in same state of any DFA. Then in this situation, I can say that there is the language is non-regular. Okay, so now before so this was the question we have taken. I gave you this question as a homework. Did you try this? Okay, so this we will see after some time. This question we will see after some time. So let's remove this. And the remaining questions, did you try? Tell me. So before that, let me tell you few important things. So let's one by one, let's see the concepts. So now, can you notice what was happening? Let's see. Let's revisit. Let's revisit this language. Let's revisit this language. This language, let's revisit. A power n, b power n, where n is greater than equal to 0. Let's revisit this language. Okay. Now you tell me here, for this language, what was our set as? Infinite set we have taken, right? For this language, we have taken this set as. This set as we have taken. Like I can say a power n, where n is greater than equal to 1. This set we have taken. Okay. Now, why this set we have taken? What is the reason this set we have taken? What is the reason? Let me tell you the reason. Let me tell you the reason. This set is, I can say, in this set, what happens? That every two strings, they, okay, they cannot go to same. Basically, whatever two strings you take, they should go to different states. Okay. So here, what happens? Let me tell you what happens here. So here this happens that take any two string. Tell me which two strings should I take? Okay, take any two string. For example, a power 1 and a power 3. Okay, so take any two string. Then what will happen? Take any two string. So take any two string. If they go to same state, for example, a power 1, a power 2, if they go to same state, okay, let us assume they go to same state, because there are infinite number of strings. Yes or no? There are infinite number of strings. This is an infinite set. So you can notice, because we have infinite number of strings and the DFA has only finite number of states, so the DFA should go to, I can say, for at least two strings, DFA should go to same state. Okay, for at least two strings in this set, for at least two strings, DFA should go to same state. Okay, now you can notice, if DFA goes to same state on these two strings, then there is a problem. Okay, and who will create the problem? Can I say that this will create the problem? Can I say b power 10 will create the problem? Can I say this extension will create the problem? Can I say this extension will create the problem? No problem. You can directly go to non-final state. There is no problem. So can you notice, every extension cannot create a problem? Can you notice? Every extension cannot create a problem? So I can say there exists an extension. I can say there exists an extension who will create problem. There exists extension who will create problem. For example, who is that extension? I can say b power 2 will create problem. This b power 2 will create problem because you can notice what will happen. If this is final, then problem. If this is non-final, then problem. If this is non-final, then there is a problem. And what is the problem? That a power, I can say a power 2, b power 2 rejected. Okay, rejected. Should I reject this? Should I reject this string? This string is in the language, so there is a problem. So this is the problem because I should not reject this. And similarly, if I make this final, then also there is a problem because now a power 1, b power 2 accepted. Now this is accepted. Okay, so I can say again there is a problem. Again there is a problem. Okay, so this idea, if you notice, in this idea what we have done, we have proven that if any two of them go to same state, there is a problem. Okay, if any two of them go to same state, then there is a problem. So what we have proven? So we have proven that. So we have proven that. Okay, from S. Okay, so we have proven that from S, if any two string go to same state, if any two string, okay, you can take any two string. Remember, you can take any two string. So if any two string go to same state, okay, go to, or I can say and in same state, then there is a problem. Then there is a problem. Okay, now what we will do? Now we will take another method. Okay, now let me take another method. So in this method, let me take another method. What I will do? I will prove that these strings, I can say every two of them are distinguishable by some extension. Can you notice? So there is some extension. Any two of them, actually, if you take any two of them, a power m, a power n, any two of them where m is not equal to n, then if you take any two of them, then there is an extension. If you take any two of them, then there is an extension. There is an extension such that what will happen? Tell me. Such that there is an extension such that one of them will go to final, one of them will belong to L, and one of them will not belong to L. This is what is happening. Yes or no? Can you notice? This is what is happening. Please notice. This is what is happening. Okay, there is an extension. Like for example, this extension. Now you can notice one of them belongs to L, one of them does not belong to L. Okay, yes or no? Like for example, there is an extension N, such that this actually belongs to L, this does not belong to L. Correct or not? Are you getting my point? What I'm saying? So I'm saying that basically, or you can think like this, that one of them goes to final state, one of them goes to should go to non-final state. One of them should go to final state, one of them should go to non-final state. So I can say one of them should belong to L, and one of them should not belong to L. Correct? This is, then in this situation I can say these two strings are indistinguishable. Then I can say a power m, a power n are indistinguishable, means are distinguishable. They are distinguishable, means distinguishable. Then you can call them distinguishable. Okay, so let me explain. Don't worry about it. This is a very easy concept. What I'm saying that if you take any two strings, then there is an extension. Tell me which is that extension. Tell me. There is an extension. Which is that extension? For example, you can take b power m. Which is that extension? You can take b power m. You can take this b power m. Now you can notice that if you take this b power m, then what will happen? Then this will happen. A power m, b power m, this belongs to L, and a power n, b power m, okay, this does not belong to L. So in this situation, I can say that, okay, there exists extension. So I can say they are distinguishable. Okay, so this is the idea. Let me summarize this. So what is happening here? what is happening here? Let me summarize this. You tell me, assume there is a DFA. Okay, assume there is a DFA. You just tell me this part. Okay, assume there is a DFA. Assume D is DFA. Okay, now assume there are two strings. Okay, consider there are two strings. Consider only two strings you consider. Consider two strings W comma U. Okay, consider two strings W comma U. Okay, just consider two strings W comma U. Okay, such that W comma U, such that there exists a Y, such that there exists another string. There exists another string which is extension. We will call it extension. Okay, there exists another string. There exists another string such that okay, there exists another string. So let's call it, there exists another string Y. There exists another string Y such that WY, okay, belongs to L and UY does not belong to L. Okay, UY does not belong to L. So one of them, basically, one of them belongs to L and one of them does not belong to L. Okay, so are you getting my point? What I'm saying? I'm saying assume there is a DFA. Assume there is a DFA. Consider two strings. Consider two strings W comma U. Any two string you can consider. Any two string you can consider. Okay, any two string such that there exists extension. There exists extension Y such that WY belongs to L and UY does not belong to L. Then my question is, can DFA-D go to same state on W comma U? Can DFA-D go to same state on W comma U? Tell me, can DFA-D go to same state on W comma U? Can DFA-D go to same state on W comma U? The answer is no. The answer is no. Why? What is the reason? What is the reason? See, very simple reason. Very simple reason. What is happening? So two strings you have. So W comma U, two strings you have. This is your W. This is your W. Okay. And let's assume this is your U. So two strings you have, W comma U. And there is extension. There is extension Y. There is extension Y such that this WY belongs to L and this does not belong to L. Okay, so this is the situation. Please notice, this is the situation. Yes or no? Correct? This is the situation. This type of strings these are. Now, can any DFA go to same state on W comma U? On W comma U. Now, the answer is no. The answer is no. Okay, because if, okay, by for contradiction, you can prove by contradiction. You can prove by contradiction. You can prove by contradiction. So how will you prove by contradiction? If DFA, if some DFA, any DFA, I don't know which DFA, if some DFA goes to same state on W comma U, then what will happen? Tell me. Then what will happen? If some DFA goes to same state, some DFA D you have, and it goes to same state on W comma U, on W comma U, it is going to same state. Let us assume. So for contradiction, I am proving by contradiction. I am saying that if some DFA goes to same state on W comma U, now there is a problem. What is the problem? Tell me. Who will create the problem? Where this Q will go on Y? Where this Q will go on Y? Then there is a problem. Where this Q will go on Y? This extension Y will create the problem. Where this Q will go on Y? Tell me where this Q will go on Y. Where this Q will go on Y? There is a problem. There is a problem. Okay, there is a problem. Because if you go to non-final, there is a problem. What is the problem? If you go to non-final, then you can notice what is the problem if you go to non-final. Remember, WY belongs to L. Remember, WY belongs to L and UY does not belong to L. Remember, Remember, wy belongs to L and uy does not belong to L. So tell me, what will be the problem? Yes, wy rejected. So if you go to non-final, what is the problem? Just only tell me the problem. The problem is wy rejected. Wy rejected, but wy belongs to L. Wy belongs to L, but you are rejecting it. You are rejecting it. Similarly, if you go to final, there is a problem. If you go to final, there is a problem. What is that? Uy accepted. Uy accepted. There is a problem. So whatever you do, there is a problem. Yes or no? So can I say that these type of strings cannot go to same state in any DFA? In any DFA, this type of strings cannot go to same state. Yes or no? So, okay, such strings w comma u, you are called, such strings w comma u are called, what we call them? We call them distinguishable. Basically, these are the Fumfaji. Yes or no? They cannot go to same state. Okay, in any wedding, you can take any wedding. You can take any wedding. These are the Fumfaji, Jijaji, okay, Chachaji. So they can never. No, not Chachaji. Chachaji are good. Chachaji, Mamaji, these are good people. But Fumfaji, Jijaji, some, okay, from the other family. Okay, so these people are the actual villains. Okay, so you can notice that. So such strings w comma u are called distinguishable. Distinguishable strings. Strings with respect to L. With respect to L. Okay, with respect to L, these are the distinguishable strings. Is this clear? So these type of string, we call them distinguishable strings with respect to L. With respect to L, these are distinguishable strings. Please tell me, did you get it? Did you get this? Let me ask you some questions. Let me ask you questions. Okay, let me give you some language. Consider this language. Consider this language. Okay, so any language, regular, non-regular, any language you can take. Consider this language. Let me consider ending with 0. Okay, consider this language ending with 0. Okay, now you tell me which pair of strings are. Let me give you the summary. What is the summary? When do we call strings are indistinguishable? What is the summary? What is the summary? Summary. So there is a language. First of all, you must have a language. Language L is there. Okay, and w comma u comma y, they belong to sigma star. They do not, okay, they need not belong to L. They can belong, they are basically any string. Yes or no? W comma u comma y, they are any string. There is a language, but they are any string. Now w comma u are called indistinguishable. Sorry, you are called distinguishable, means different. Distinguishable. Okay, if and only if there exists a y, such that there exists a y such that one of them will go to final, one of them will go to non-final. Yes or no? Such that one of them belongs to L and one of them does not belong to L. One of them belongs to L, one of them does not belong to L. Yes or no? One of them belongs to L. I can say exactly one of them belongs to L. Can I say? I can say such that exactly one of them, or I can say one of wy belongs to L. One of wy comma uy belongs to L. Other does not belong to L. Did you understand this? In this situation, this is called distinguishing extension. In this situation, what we call this y, what name we give to this y? This y is the distinguishing extension. This y is distinguishing. Okay, so this y is called distinguishing extension. Okay, actually this is happening. So you have some language L. There is some language L, and you take any strings from sigma star. Okay, from language or not, you take any two string, any two strings you take from sigma star. So let's assume this is your w, and let's assume this is your u. Okay, now what happens? So there exists extension y. There exists this extension y such that one of them goes to one of them belongs to L and other does not belong to L. One of them belongs to L. Remember, one of them belongs to L, one of them belongs to L, and another does not belong to L. Okay, then we say that W comma U are distinguishable by L. Is there any role of L? See, these are from sigma star. In this definition, is there any role of L? Is there any role of L in this definition? Is there any role of L in this definition? Is there any role of L? Yes, there is. Yes, here is the role of L. So string you can take any. String you can take. You can take any string you can take. U comma WU. You can take any two string. Okay, and there exists an extension. There exists Y. Remember, there exists Y. You can take any two string you can take. Okay, there exists a Y. There exists a Y such that there exists a Y such that one of them will go to L and one of them will not go to L. Okay, one of them belongs to L, one of them does not belong to L. Then W comma U are called, they are called distinguishable by L. We call them distinguishable by L. And this Y is called what? This is called distinguishing extension. This is called distinguishing extension. Okay, in short, remember this dist simply means distinguishing. So I'm using this dist means this dist. Whenever I write this dist, what it means? It simply means distinguishable. It means distinguishable. I will not write this again and again. And similarly, if I write indist, then that means indistinguishable. Or equivalent. Okay, anyway, so this definition is clear to everyone. Please tell me. Okay, let's do some practice. With practice makes you perfect. So let's take this. Let's take this language. Okay, now in this language, which strings are distinguishable? Which pair of strings are distinguishable? Okay, which pair of strings are distinguishable? So some strings I'm giving you, and you tell me which strings are distinguishable. The first, okay, so tell me, A, B, A, B, B, B. Are they distinguishable? Are they distinguishable by? Okay, they are. Who is the extension? Who is the distinguishable extension? Okay, let me take another. A, B, 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 A, A. Let me take another. A, B, A, B, B, A. Okay, so tell me about this one. First, to tell me about this one. Which of them are distinguishable? So who is the distinguishing extension for them? Okay, who is that distinguishing extension which will take this to L, one of them to L, another to out of L? Tell me. Yes, so these are distinguishable. These are distinguishable. And by whom? Distinguishable, like who is the extension? By extension? By which extension? By which extension? Very simple, empty string. By empty string, yes or no? They are okay. This extension is fine. This extension is fine. You can take this extension also. Can I take this extension also? Can I take this extension also? So I can take this extension also. Correct? So they are distinguishable. Okay. Now tell me about these two. Are they distinguishable? Yes. Again, by which extension? By which extension? Empty string. Or I can take A. I can also take A. Yes or no? I can also take A. Are they distinguished? Can I say the extension B? Sorry, A I cannot take. And B also, oh, sorry. Here also B I cannot take. Okay, the extension B will not work. The extension B will not work. See, extension B will not work. Extension B will not work. So empty string, this will work. This empty string will work. Extension B will not work. Okay, extension A will not work. Extension A will not work. Apart from this, any other extension will work or not? Apart from this, any extension will work or not? Will not work. this extension will work. This is the only extension. Okay, this is the only extension, I can say, only possibility. This is the only possibility. What about these two? They are also okay. This extension epsilon. Is this clear to everyone? What is happening here? See, okay, if you see this empty string, then one of them is going to L and one of them does not belong to L. Similarly, you can notice one of them belongs to L, one of them does not belong to L. Similarly, what about these two? What about these two? There is no extension. Yes or no? Can you notice there is no extension? So these are not distinguishable. There is no extension. No extension can distinguish them. No extension can distinguish. No extension can distinguish. No extension can distinguish. So in this situation, we will call them equivalent. If no such extension, okay. So remember, if I can say if, okay, and this is the definition of, I can say, equivalent strings. This is the definition of equivalent strings. What is the definition of equivalent strings? When can I say two strings are equivalent or indistinguishable? When can I say two strings are equivalent? Two strings are equivalent. I can say there is a language L. There is a language L. You take any two strings, W, U. You take two strings, then W, U are called equivalent. They are called equivalent. They are friends. They are friends. If, okay, they are friends in any situation. If one of them is going to L, then another will also go to L. So they are equivalent. I can say they are friends. They are J Viru. They are J Viru. This is W. This is U. Okay, this is U. Now, whatever Y you take, whatever extension Y you take, for all Y, whatever Y you take, for all Y, whatever Y you take, for all Y, what will happen? Either, either both will go to L, either both WY, UY belongs to L, or both does not belong to L. Have you seen this type of situation in any previous topic? Have you seen this type of situation in any previous topic? This type of definitions, equivalent states. Yes, we have seen this type of situation when we saw equivalent states in DFA. Equivalent states in DFA. Do you remember equivalent states in DFA? This type of situation we have seen equivalent states in a DFA. In a DFA, when do we say two states are equivalent? Two states are equivalent. You have a DFA. In that DFA, when can I say two states are equivalent? You have a DFA. Okay, you have a DFA D. Then you can notice state Q1, Q2. Okay, state Q1, Q2 are called equivalent. When are they called equivalent? Okay, they are called equivalent if and only if for all strings W, if, okay, whatever string you take, for all string W, remember, for all string W, okay, so this will go to final. I can say this Q1 will go to final. Okay, this Q1 belongs to final. I can say this Q1 will go to final if and only if this Q2 goes to final. Do you remember this? If and only if this Q2 goes to final, means either both will go to final. For every string, either they both will go to final or both will go to non-final. So the same situation is happening here. Yes or no? The same situation is happening here. Two strings are equivalent. Two strings are friends. When can I say two strings are friends? I can say you have string W, U. Okay, when can I say these are friends? So this is W. Okay, this is U. Now you can notice in any situation, if some situation comes, thus in the same situation, what they will do? Either they will both go to jail. See, either they both do not belong to L, or okay, or they both belong to L. Either they both do not belong to L, or they both belong to L. Okay, so you can notice in this situation, I can say that W, U are friends. Yes or no? W, U are true friends. These are the true friends. And this is what, this is called the situation. Okay, this is called the test, or I can say situation. Basically, this is your extension. Actually, there is basically, I can say for every string, this is the situation, this is the test of friendship. Okay, anyway, so what I'm saying that if you have any two strings, then for all y this should happen. Okay, for all y, if this happens, for all y, whatever string you take, either both will go to either both will belong to L or both will not belong to L. Whatever L you take, okay, then we will say that these are friends. Okay, it will never happen, that for some y, okay, one of them is going to L, one of them is not going to L. This will never happen because these are true friends, equivalent. So in this situation, we will call them equivalent. So you can notice here, look at this example. In this example, you can notice that this ABA, look at these strings, ABA, and another string you look, that is a BBB. Now these two strings with respect to L, remember your L is what? Your L is ending with A. Your L is ending with A. Okay, this is your language and L that is ending with A. Now you can notice these two strings are distinguishable by whom? Like this string, this string. You can notice that there is some extension. Which extension? Empty string. There is some extension such that what will happen? This will belong to L, and you can notice this will not belong to L. There is some situation. So what I can say? So I can say these are not true friends. So I can say these are not true friends. I can say these are distinguishable. I can say these are distinguishable strings. Correct? Now, similarly, if you notice, if you take this example, like this ABA, BBA, okay, ABA, BBA, look at this, ABA, BBA. Now, in this situation, what will happen? ABA, BBA. Now, whatever string you take, what will happen? Tell me. Whatever string you take, what will happen? Whatever string you take, please tell me what will happen. Whatever string you take, either both will go to final, either both will belong to L or both will not belong to L. Whatever string you take, you can take any string you want. Okay, you can notice both are belonging to L. And if you take this string, for example, if you take this string, like if you take this string BB, if you take this string, then what will happen? If you take this string, then what will happen? They both will not belong to L. So for any string, either they both belong to L, or for any string, either they both belong to L or both do not belong to L. So this is the idea. So I can say these are equivalent. Okay, these two are equivalent. Is this clear to everyone? Please tell me. Let's see another example. Let me ask you another example. So let me ask you this fourth. This empty string, comma a power 100. What about these two? What about these two? Next, a b a b b. Okay, b a b b a. What about these two? So can I say they are equivalent? Can I say, is there any extension? Is there any extension? Is there any extension which can, okay, there is no extension, right? There is no extension. There is no extension. These are equivalent. Okay, so these are, I'm asking distinguishable. These are actually equivalent. These are actually equivalent. Sorry, let me check. Oh, sorry. These are not equivalent. Sorry. These are distinguishable by empty string. Okay, sorry. So by extension, empty string. By extension, empty string. By extension, empty string. So these are also distinguishable because they are distinguishable by extension, empty string. One of them will belong to L, another will not belong to L. Okay, one of them, like, okay, if you see this extension, then one of them will belong to L. Like, okay, this is the idea. This is, okay, U is a power 100. Now you can notice this is W, which is equal to epsilon. Okay, this is U, which is equal to a power 100. Now you can notice if you see this extension, look at this extension, then what will happen? This will not belong to L, this will belong to L. So I can say these two people are not true friends. I can say these two people are distinguishable strings. These are distinguishable strings. Okay, next, what about this one? What about this one? Okay, they are also distinguishable. Okay, by extension, empty string. By extension, empty string. So tell me one thing. Tell me one thing. for this language, you tell me one thing. Can you notice one very interesting thing will happen? Can you notice? Can you create infinitely many distinguishable strings? Can you create infinitely many distinguishable string? Infinitely many distinguishable string for this language L. Can you create? Can you create infinitely many distinguishable strings which are pairwise distinguishable? Means infinitely many pairwise distinguishable, infinitely many pairwise mutually distinguishable strings. Can you create? Tell me, can you create? The answer is no. Okay, the answer is no, you cannot create, because you can notice for this language what will happen. For this language actually, if you notice all the strings, look at all the strings. Okay, just look at all the strings. Look at all the strings. So when I look at all the strings, should I look at the strings of L or should I look at all the strings? Should I look at strings of L or should I look at all strings? I should look at all strings of sigma star. Look at all strings of sigma star. Just look at them. Okay, then what will happen? These all strings of sigma star, you can notice they will go to two categories. Okay, they will actually, because of this language L, due to this language L, what will happen? Due to this language L, two categories will be created. Two categories will be created. This category will have ending with A. This category will have ending with A, and this category will have not ending with A. This category will have ending with A, and this category will have not ending with A. Yes or no? So two categories will be created. Here you have all the strings which are ending with A. Here you have all the strings which are ending with A. And here you have all the strings which are not ending with A. Did you get it? Please tell me. Can you notice? Can you notice? Please, can you notice? These are equivalent. All these are equivalent. Yes or no? Can you notice all these are equivalent? All of them are equivalent. If you take any two of them, any two, okay, any two string which are ending with A, any two string you take which are ending with A, any two string which are ending with A, take any two string which are ending with A. Now you can notice whatever extension you put, what will happen? Tell me what will happen. Whatever extension you put, whatever extension Y you put, either both will go to either both will belong to L or both will not belong to L. Yes or no? Either both will belong to L or both will not belong to L. So this will happen. Whatever extension you take, for all Y this will happen. Okay, so for these two, you can notice for all Y this will happen. For all Y this will happen that either both will belong to L, either both will belong to L, or both will not belong to L. Yes or no? Whatever you put, either both will belong to L or both will not belong to L. Similarly, those strings, these strings are also equivalent. So can you notice? Can you notice? Please notice one thing. So can you create infinitely many Fufaji? Can you create infinitely many pairwise distinguishable strings? You cannot create. You cannot create. Yes or no? So that is the reason. That is the reason this language is regular. Why this language is regular? Let me tell you. Because you only have to take care. These people are equivalent. See, these people can accommodate. Okay, adjust kar lenge. These people will adjust together, and these people will adjust together. So how many rooms you need? Tell me. How many rooms you need? How many rooms you need? These people will handle. They will adjust together. They will adjust together. So you only need two rooms. That is okay, and that is your DFA. Can you notice? You only need two rooms. Okay, you only need two rooms. One is not ending with A. One is not ending with A. Okay, all the strings which are not ending with A will be in this room, and all the strings which are ending with A will be in this room. Okay, so you only need two rooms. You only need two rooms. In this room, you have all the strings which are not ending with A. You have all the strings which are not ending with A. And in this, you have all the strings which are ending with A. Can you notice? So that is the reason this language is regular. This language is regular. Why this language is regular? because you can notice in this language, you can notice only two possibility you need to keep track of. And what will be the initial state? Which of them will be the initial state where you have empty string? This empty string, this room will be the this room will be the initial state, and the final state will be your L. The final state will be your L. Final state will be your L. Okay, this will be your final state. Now you can just make the transition. Now you can just simply make the transition that if A comes, you go here. Yes or no? If A comes, this will go. This will become BA BA. If A comes, this will become BA BA. If A comes, this will go here. If B comes, this will go here. If B comes, this will go here. And this is your DFA for L. Yes or no? Please tell me, did you find this interesting? Like, okay, is this clear? Alap is asking, I did not understand why we cannot create infinitely many distinguishable strings. Array, can you create infinitely many distinguishable pairwise set? Can you create an infinite set? Alap, I am asking this question. Alap, understand this question. Can you create an infinite set in which every two strings are distinguishable? Can you create an infinite set? Can you create an infinite set? Can you create an infinite set in which every two strings are distinguishable? Can you create an infinite set? Just can you create an infinite set? Can you create an infinite set in which every two strings are distinguishable? This is the question. So can you create? So the answer is no, you cannot create. Okay, so these people will adjust and these people will adjust. Okay, is this clear? In the Fir Hera Feri movie, okay, there is a movie Fir Hera Feri. In that, Johnny Lever, okay, there is a dialogue that the rassi choti hai. Then Johnny Lever says, "Hum adjust kar lenge na bhai." Okay, so you can notice only two rooms are there. These people will adjust. These people will adjust. Okay, so anyway, so you can notice. Is this clear to everyone? Please tell me. So you can notice in this language what happens. In this language, you only need to take care of two states. You only need to keep track of finite number of possibilities. Can I say? Okay, I hope you are finding this quite interesting. Okay, let's take some more examples. Let's take some more example. Consider this example: a power n, b power n, where n is greater than equal to 1. Okay, maybe n is greater than equal to 0. Let's take n is greater than equal to 0. Now you tell me in this language which strings are distinguishable. Okay, this is your language. Some questions I am asking you back to back. So first you tell me which strings are distinguishable. Which strings are distinguishable? Okay, some strings I am giving you. So first string, for example, a power 2, a power 10. Second string, b power 10, b power 20. Okay, so tell me first you tell me about these. Are they distinguishable? Are they distinguishable by whom? Who is the extension? Which extension will distinguish? Which extension? By which extension? I can say b power 10 or b power 2. Okay, I can say b power 2 or b power 10. So this extension. So these are distinguishable. These two are distinguishable by this extension. What this extension will do? Okay, one of them will belong to L, one of them will not belong to L. Okay, so this is your extension. What is the okay? What about these two? What about these two? What about these two? They are equivalent. They are actually equivalent. Can you notice they are equivalent? Whatever you put in front of them, look at this: b power 10, b power 20, b power 10, b power 20. What will happen? Whatever you put in front of them, this is your b power 10, this is your b power 20. Whatever you put, whatever y you put, what will happen? Tell me. Either they will both belong to L or they will both not belong to L. Whatever y you put. For example, if I put this y, for example, let me put this y, b power 100. Let me put this y, b power 100. Then you can notice both will belong to L. Okay, let me put this. Now similarly, if I put this BA, then what will happen? If I put this BA, then both of them will go out of L. So whatever you put, either they will both belong to L, or they will both not belong to L. Is this clear? See, please understand one more thing. Now don't say final or non-final. Now don't say final or non-final. Now I'm discussing language. The concept that I'm discussing now, that is only for the language. Now we don't care about BFA. Okay, this concept is only with respect to language. You have language, with respect to language, this concept we have. Is this clear? With respect to this language, the concept we have. So these two are equivalent. What is the problem? Oh, sorry. So both will not belong to L. Okay. So whatever you do, they will, I can say they are distinguishable. Why? Sorry, they are equivalent. They are equivalent. Why? What is the reason they are equivalent? They are equivalent because whatever you put, this is your b power 10, this is your b power 20. For all y, what will happen? Whatever y you put, what will happen? Tell me. Whatever y you put, they do not belong to L. For all y, you can notice. So that is the reason they are equivalent. Okay, that is the reason they are equivalent. Okay, next. So this, now let's see the next. So which strings are distinguishable? This was our question. Now which strings are equivalent? Okay, let me give you some more options. Find distinguishable strings. Okay, so let me give you some questions. Third option, a power 10 b power 20. Fourth option, a power 10 b power 20, a power 10 b power 5. Next, a power 10 b power 20, a power 20 b power 40. Next, a power 10 b power 8, a power 5 b power 3. Okay, so tell me, which of them are distinguishable? Which of them are distinguishable? Are they distinguishable? These two, are they distinguishable? Yes, they are distinguishable. They are distinguishable by which extension? Which extension will distinguish them? Which extension? B power 5. B power 5. Okay, B power 5. Not A power 10. Can I say A power 10? Can I say A power 10? No. Okay, no. A power 10 cannot distinguish. If you put A power 10, then what will happen? If you put A power 10, then what will happen? Both are not in L. Both are not in L. Both are not in L. So this is your L. So extension B power 5 will work. What about, okay, don't say accepted, rejected. Just say in L, not in L. Don't say accepted, rejected, non-final, final. Just say with respect to L, we are looking. We are looking with respect to L. Now tell me, A power 10, B power 20, A power 20, B power 40. What about these two? What about these two? They are equivalent. They are equivalent because whatever you put, they will never belong to L. I can say. Okay, whatever you put, for all, they do not belong to L. For all, they do not belong to L. Okay, so next, what about these two? A power 10, B power 8, A power 5, B power 3. Again, these are equivalent. Yes or no? There is no extension. Again, these are equivalent. Is this clear? Okay, is this clear? Again, they are equivalent. Next. So, like, this is the idea. Now tell me. Okay, let me ask you another. Now consider this set. What about empty string? We have empty string, comma A. What about empty string with empty string? Who is equivalent with empty string? With empty string, which is equivalent? Give me something which is equivalent to empty string. Give me something which is equivalent to empty string. Find equivalent string. Find equivalent string to given string. To given string. Find equivalent string to given string. Now tell me. And for empty string, which string will be equivalent? For empty string, can you find something? for empty string? Can you find something? Tell me. Something can you find? Nothing, right? Yes or no? Nothing is equivalent to empty string. Nothing is equivalent to empty string, correct or not? There is nothing which is equivalent to empty string. Yes or no? Nothing is equivalent to empty string. Whatever you do, okay, nothing is equivalent to empty string. So the answer is nothing. No string is equivalent to empty string. Correct? Is this clear to everyone? Because if you put any string, then what will happen? Okay, if you put any string, then you put AB, then distinguishable by AB. Yes, very good. If you put any string, W, then what will happen? This epsilon comma W, this extension will distinguish. This extension will distinguish. Yes or no? This extension will distinguish. So there is nothing here. Okay, what about this? For this A power 10, B power 5, give me something which is equivalent to this. Give me something which is equivalent to this. A power 10, B power 5. Is it equivalent to B power 5? Is this equivalent to B power 5? Is this, can I say, is this equivalent to B power 5? Can I say B power 5? No, I cannot say B power 5. These are not equivalent. So the answer will be very good. Yuvraj, very good. Okay, anything of this form, A power 15, B power 10, this will work. Basically, anything of this form, okay, anything will work like this. Anything of this form will work. Every string of this form will work. Is this clear to everyone? Please tell me. Anyone has any doubt in this? In this concept, anyone has any doubt? Now the next question. Can you find a set? Find a set which has, so find a set. Okay, this type of set you find. What you do? You find an infinite set. Find an infinite set of equivalent strings. Find an infinite set of pairwise equivalent strings. Find an infinite set of pairwise equivalent strings. Pairwise equivalent strings. Can you find infinite set of pairwise equivalent strings? Can you find such set? Can you give me a set? Yes, you can give me. For example, you can give me this set. You can give me. Okay, consider this set. Like I told you, like A power n, B power n minus 1. Consider this set. N is greater than equal to 1, or maybe n is greater than equal to, yes, n is greater than equal to 1. So you look at this set. Find an infinite set in which pairwise equivalent. In this you can notice these are pairwise equivalent. Can you notice? Like in this you have A power 1, okay, A power 2, B power 1, A power 3, B power 2. Okay, they are pairwise equivalent. All of them are equivalent. Can you notice? All of them are equivalent. All of them are equivalent. Yes or no? Is it clear to everyone? All of them are equivalent. You can also give me this. For example, A power n, B power n, A power m. Okay, you can also give me this. They are also pairwise equivalent. Yes or no? They are also pairwise equivalent. Tell me. So these are pairwise equivalent strings. Like this you can give. I hope this point is clear. Now you give me pairwise distinguishable strings. Now you give me infinite set in which you have pairwise distinguishable strings. Infinite set of pairwise distinguishable strings. Can you give me? So the answer will be what? For example, this type of set. Remember, this type of set we call it S. This type of set we call S. Correct or not? This type of set, what name we give to this? We call it as like infinite set of pairwise distinguishable strings. This type of set we call it as. So what you can give me, tell me? A power n. Can you notice this a power n? In this set, every two strings are, in this set you can notice every two strings are distinguishable in this set. Yes or no? Whatever two strings you take, they will be distinguishable. Okay, any other example? Any other example? Any other example? What is that? Give me some other example. Can I say a power n? Okay, so this a power n is one example. In this set, all do not belong to it. No, we do not. Okay, see, this set, in this set, every two strings are distinguishable, right? Every two strings, you take any two strings, they are distinguishable. Any two strings you take, they are distinguishable. By whom? They are distinguishable by whom? For example, they are distinguishable by b power 10. So you can notice this belongs to L, this does not belong to L. So whatever two strings you take, they are distinguishable. Is this clear, Yuvraj? So whatever two strings you take, they are distinguishable in this set. In this set, every two strings are distinguishable. Okay, let me ask you this set. A power n b. A power n b. What about this set? Where n is greater than equal to, where n is greater than equal to 0. What about this set? Can I say every two strings are distinguishable? Pairwise distinguishable, can I call them? Can I call them pairwise distinguishable? Like you have B, you have AB. Are they distinguishable? B, AB. Yes, they are distinguishable. Okay, what about AAB? See, these two are distinguishable by empty string. These two are distinguishable by empty string. So I can say these two are distinguishable. Okay, and you can notice, what about B, what about these? So these are distinguishable by whom? These are distinguishable by whom? Tell me. So you can notice these are distinguishable by empty string. These are distinguishable by B. What about these two? What about these two? These are distinguishable by whom? These are distinguishable by B. Yes or no? Can you notice in this set, every two elements are distinguishable. In this set also, every two elements, whatever two elements you take, they will be distinguishable. Is this clear? Okay, so very simple. I hope this point is clear. So you can create many, I can say set of distinguishable strings you can create. So like this. Can you give me something else? Can you give me something else? If I create b power n, if I create b power n, where n is greater than equal to 1, in this situation, what will happen? If I create b power n, they are pairwise equivalent, yes or no? Can you notice they are pairwise equivalent? They are pairwise equivalent strings. Okay, pairwise equivalent. Every two of them are equivalent, I can say. Okay, so anyway, this is the idea. So you can notice for this language, you can find, okay, we can find at least one, or I can say we can find some set of, we can find some infinite set of distinguishable strings. We can find some infinite set of distinguishable strings, pairwise distinguishable strings. Pairwise distinguishable strings. So what I can say, for this language, we can find some infinite set of pairwise distinguishable strings. So L is what? So L is non-regular. Yes or no? So L is non-regular because we have infinite set. We have infinite set of pairwise distinguishable strings. Pairwise distinguishable strings. So this L is non-regular. Is this clear to everyone? This language is non-regular because all you have to do, just give me this infinite set in which every two elements are pairwise distinguishable. You can notice this is infinite also. You can notice this is infinite set also. And you can notice these are pairwise distinguishable. These are pairwise distinguishable by L. Okay, with respect to L, I can say. they are pairwise distinguishable by L. So because because this exists, because this type of set exists, okay, so I can say L is non-regular. So this L is non-regular because this type of set exists. Pairwise, infinite set of pairwise distinguishable strings. This type of set exists, so this is non-regular. Is this clear to everyone? Tell me. Because we have to keep track of infinite possibilities. Okay, let's take these questions. These questions I gave you as a homework. Now let's take back to back. So this first question we have done, correct? The first question we have done. The second question also we have done. So for the first question, I asked you two things. I asked you. For the first question, 0 power. In this question, what was the homework? Like for every language, find two set. Okay, find two set S, which will work basically. Okay, so this is the question. What is the? Let me ask you. This is the question that for each find some. For each you find some infinite set of pairwise distinguishable strings. Pairwise distinguishable strings. Is this clear? For this, for each of them, you find some infinite set of pairwise distinguishable strings. So for the first one, we have already done. Many you can find for the first one. Okay, let's call it first one. So for the first one, what you can do? Your language is 0 power 1, 0 power n, 1 power n, where n is greater than equal to 0. So for this, you can very easily you can find S. For example, this set you can find 0 power n, where n is greater than equal to 0. Okay, this set you can find. You can also find another set. You can also find another set. Another set, for example, I can say 0 power n, 1. This set also you can find. Yes or no? N is greater than equal to this, or n is greater than equal to 0. It does not matter. Correct? So like this you can find. So, okay, like this you can find two set. So these are the infinite set of, I can say these are the infinite set of pairwise distinguishable strings. Infinite set of pairwise distinguishable strings. Pairwise distinguishable strings. Can you also give me infinite set of pair? Okay, let's call this set P. Let's call this set P. Pairwise equivalent strings. Pairwise equivalent strings. For example, I can say 0 power n, 1 power n minus 1. 0 power n, 1 power n minus 1. Look at this set. Okay, look at this set. So this set is actually infinite set of pairwise equivalent strings. Of pairwise equivalent strings. Okay, so like 0 power n, 1 power. Look at this set. 0 power n, 1 power n minus 1. Look at this set. N is greater than equal to 1. If you take any two strings from this set, if you take any two strings from this set, then you can notice they are okay, they are equivalent, right? They are equivalent, because if one comes, then if one comes, all of them will belong to L. If one comes, all of them will belong to L. Okay, so you can notice if one comes, okay, if you put this extension 1, if you put this extension 1, then what will happen? If you put this extension 1, then all of them will belong to L. All of them will belong to L, correct? All of them will belong to L. And if you put something else other than 1, if you put something else, tell me, something else other than 1, something else other than 1 if you put, then what will happen? Something else other than 1 if you put, like for example, something else other than 1. No. Other than 1. For example, if I put 0 power 2, 1 power 3. If I put this 0 power 2, 1 power 3, then for this, what will happen? Okay, so this 0 is not equivalent to all of them. So I should not say this 0. Okay, from this set, I should remove this. So this should be n greater than 2. This should be n greater than equal to 2. This should be n greater than equal to 2. This 0 should not be there in this set. Correct? Yes or no? See, because this 0 is not equivalent to them. Yes or no? This 0 is not equivalent to them. You can notice this 0 is not equivalent to them. This will belong to L, but this will not belong to L. So this 0 is not equivalent to them. This 0 is not equivalent to them. Okay, so this 0 is not equivalent to them. So what I can do? I can put this 2 here. Now everything is fine. Now everything is fine. If you give 1, all of them will belong to L. Okay, and if you give anything other than 1, if you give anything other than 1, any string other than 1, if you put, okay, if you put any string other than 1, then they will all go out of L. Okay, so this is the idea. So I can say they are pairwise equivalent strings. So here actually, when we were finding pairwise equivalent strings, this b power n, a power n b, these are distinguishable, these are distinguishable. In the equivalent strings, so this should be, I can say this should be n greater than 2. Okay, so this actually should be n greater than equal to 2. Okay, let's move on now. Okay, so let's see the next. What is the next language? So this language is done. What is the second language? Equal number of zeros and equal number of ones. Equal number of zeros and ones. For this language, the second language, equal number of zeros and ones. Okay, equal number of zeros and ones. Then tell me, for this, which set will work? This set, remember this set is called distinguishing set. Give me a distinguishing, infinite distinguishing set. Give me a distinguishing set, infinite distinguishing set. Infinite distinguishing set. So for example, this set you can again the same set, 0 power n, where n is greater than equal to, where n is greater than equal to 1. This set will work. Correct? This set will work. Okay, this set will work. Can you give me some other set? Some other set which was not working in the first language. Some other set which was not working in the first language. Some other set. For example, I can say 0 power n, 1 power n, 0 power n, 1 power n, where n is greater than equal to 1. 0 power, okay. This set, look at this. I think not this set. Okay, so here actually, these two strings, are they distinguishable? Look at these two strings. Are they distinguishable or not? Are they distinguishable? Already, okay, if you, whatever you put, already you have equal number of zeros and ones. Already you have equal number of zeros and ones. So whatever you put, what will happen? So whatever you put, what will happen? Either both will go to, okay, yes or no? See, whatever you put, what will happen? Whatever you put, what will happen? Either they will both belong to L, or they will not both belong to L. Correct? Either they will both belong to L, or they will both go out of L. Because already very simple. Already you have equal number of 0, 1. Already you have equal number of 0, 1. So on which it will depend where they will go. They will belong to L, or they will not belong to L. On which it will depend? Tell me. On which it will depend? It will depend only on Y. It will depend only on Y. Correct or not? Yes or no? So it will depend only on Y. So that is the reason I can say that this is not correct. So let me remove this. Now this will do. Now this is correct. 0 power n, 1 power n, 0 power n. Now this is correct. Now what will happen in this situation? If you have 0 power n, 1 power n, okay, and 0 power n, and another you have 0 power m, 1 power m, 0 power m, okay, such that n is not equal to m, such that n is not equal to m, then who will distinguish them? Tell me, who will distinguish them? Which y will distinguish them? Which y is going to distinguish them? 1 power m. Which y? 1 power m will distinguish them. So this will not belong to L, and this will belong to L. So you can notice this set will work. Yes or no? Do you agree this set will work? Okay, this set was not working previously. In the first question, this set was not working. In the first question, this was set of equivalent strings. Yes or no? In the first question, for the first language, For the first language, this was set of equivalent strings, but here this is the set of non-equivalent strings. So like this you can do. I hope this point is clear. Now let's see the another. So can you notice, because there is an infinite set, because there is an infinite distinguishing set, so what I can say, this is non-regular. This is non-regular because there is infinite distinguishing set. Okay, what about this third one? WW. This is your WW, where W belongs to 0, 1 whole star. WW, this third one. WW, where W, I can say this is your language. Your language is WW. Where W belongs to 0, 1 whole star. So what is this language? First of all, you understand this language. In this language, actually, the first half is exactly equal to the second half. The first half is exactly equal to the second half. This is the first half, and this must be the second half. Okay, remember, first half must be exactly equal to the second half. Now, is this non-regular? Tell me, is this non-regular? Let's see the informal proof. This language is non-regular. This language is not regular. What is the informal proof? What is the informal proof? The informal proof is this. At any point of time, you are reading, at any point of time, do you need to remember this exact string? This string, do you need to remember? Just tell me this point. Just tell me this point. Do you need to remember this? Do you need to remember this? Yes, we need to remember this, correct? We need to remember this. Okay, this exact string we need to remember. We need to remember so that we can match after the middle. So that we can match after the middle. There is another problem. What is that? There is another problem. Can DFA find the middle of the string? There is another problem. Can DFA find middle of the string? Can DFA find middle of the string? Remember, this area is unknown. Remember, this area is unknown. This area is unknown. Can DFA find middle of the string? Remember, DFA cannot come back. DFA cannot come back. DFA can only move in this side. DFA can only move from left to right. DFA cannot come back. So can DFA find what is the middle? What is the middle point? Can you find what is the middle point? Okay, very simple point. What? Very simple. This is a track. Let's assume this is a long track. Okay, 1 kilometer, 2 kilometer. Okay, something. This is a long track. Okay, if you only walk from left to right. Okay, if you only walk from left to right, then can you find the middle of the string? You cannot go back. You cannot go back. Then can you find middle of the track? You cannot find, right? So there are two problems. The problem is, first of all, the first half must be equal to second half. First of all, you cannot find middle. You can notice finite automata cannot find the middle. Cannot find the middle position. Cannot find the middle position, first of all. So this is the first problem. Is this the only problem? Cannot find the middle position. Is this the only problem? There are more problems. What are those? More problems. Even if you find middle position, by chance, there is some, by chance some indicator is there. By chance you are in the middle position. There is another problem. What is that? You have to remember this. This you have to remember, correct? Even if you are in the middle, okay, there is another problem. Even if you are in the middle, by chance you know the middle. By chance you know the middle, okay, then also there is problem, because you have to remember this string so that you can match with this. You have to remember this to match with this. Okay, so how many possibilities are there? Tell me, how many possibilities you need to keep track of? How many things can be here? Infinite possibilities. You need to remember this, and this actually, this is, I can say, infinite possibilities. Infinite possibilities are there. There are infinite possibilities. So I can say that this language is non-regular. I can say this language, okay, where you have equal number of 0, equal number of ones. Number of 0 is equal to number of, WW. Our language is WW. So this language WW, where W is in 0, 1 whole star. This language is non-regular. This language is non-regular. And what is the problem? The problem is very simple, that there are, what are the infinite possibilities? Just tell me the infinite possibilities. What are the infinite possibilities? First of all, there is comparison, or I can say matching. There is comparison, or I can say there is matching. But give me the infinite possibilities. Give me the infinite possibilities that we need to remember. Possibilities that we need to remember. I can say these are the infinite possibilities that we need to remember. For example, can I say, for example, AB power n? Okay, like we need to remember this AB. We also need to remember AB, AB. Can I say? We also need to remember AB, 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 and so on. We need to remember them. Agree or not? Yes or no? We need to remember these possibilities. Correct? Of course. So these possibilities we need to remember. For example, this AB we need to remember. Okay, remember this AB we need to remember. At this point I'm talking about. Okay, at this point, you need to remember this AB. You need to remember AB, AB. You need to remember AB, 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 and so on. So I can say you have infinite possibilities that you need to remember. Okay, now let's see the formal proof. The formal proof is very easy. The formal proof is actually extremely easy here. So in this language, what you do, you find this set as infinite distinguishing set. Can you find infinite distinguishing set? Can you find distinguishing set? In this language, can you find infinite distinguishing set? In this language, can you find infinite distinguishing set? Yes, you can easily find the infinite distinguishing set. Actually, let me tell you one more thing. Actually, let me ask you one more thing. Let me ask you one more thing. In this, can you find two strings which are equivalent? 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 Okay, okay, don't worry about infinite. Just find two strings. Just find two strings which are equivalent. Which are equivalent. Just find two strings which are equivalent. In this language, can you find two strings which are equivalent? Two strings. The answer is not possible. Why this answer? The answer is not possible. No two strings are equivalent. In the sigma star, no two strings are equivalent. Whatever two strings you take, W1, W2, whatever two strings you take, then what you can do, who is the distinguishing people? Who is the distinguishing person? Whatever two strings you take, who is the distinguishing person? The distinguishing person is, I can say W1 or W2. I can say W1 is the distinguishing person. Okay, just put the W1, then you can notice this is the distinguishing person. Okay, W1 is not equal to W2. Actually, this may not always work. I can say this may not always work. For example, a power 4, a power 6. Can I say a power 4 is distinguishing extension? Can I say a power 4, a power 6? Tell me, a power 4, a power 6. Can I say this is distinguishing extension? No, because this is also a power 8. This is also a power 4, a power 4, and this is your a power 5, a power 5. So both belong to L. So both actually belong to L. Both of them actually belong to L. Okay. So in this situation, actually I can say, but can I say they are distinguishable, or can I say they are equivalent? Can I say they are equivalent? Tell me, can I say they are equivalent? A power 4, a power 6. Can I call them equivalent? Can I call them equivalent? No. No, I cannot call them equivalent, because you can clearly see B power 4, A power 4, B power 4. This will distinguish them. This will clearly distinguish them. Now this belongs to L and this does not belong to L. So they are not equivalent. Are you okay? Do you agree? So this may not always work, but you can notice. But basically, I am saying that whatever two strings you take, then they are not equivalent. Whatever string you take, they are not equivalent. Okay, so this is the idea. But this idea may not work. Yes or no? Do you agree? This idea may not work. This idea may not work. Do you agree? This idea may not work. Okay, so I can say whatever two strings you take, definitely they are distinguishable. Is this clear to everyone? Let me know. Okay, so very simple. So this is the idea. Now, actually, what you can do, some idea you can create. Some idea you can create that whatever string you have, whatever W1, W2 you have, whatever W1, W2 you have, which string will distinguish them, which string. So you can create this type of string. Like this type of string you can create. Uh, okay, so, okay, anyway, okay, leave it. Basically, let's leave the generalization, but you understood that whatever two string you take, whatever two string you take, they are never equivalent. Okay, whatever two string you take, they will never be equivalent. Okay, you can take any two string. For example, a power 4, a power 5. What about them? Who is the distinguishable? Which extension will distinguish them? Which extension will distinguish them? Empty string. Empty string will distinguish them. Okay, so you can take anything. I can say that there are no, I can say no two strings are equivalent. This is an interesting language, yes or no? In this language, no two strings are equivalent. No two strings are equivalent. No two strings. No two strings of sigma star are equivalent. Of sigma star are equivalent with respect to L. Okay, so if I ask you, give me infinite distinguishing set, then what you can say? Then here what you can say? Every set will work. Yes or no? Actually, every infinite set will work. Any infinite set will work. Here, any infinite set will work. You can take any infinite set that will work. Any infinite set you can take that will work in this language. For this language WW, I can say any infinite set will work. So for example, you can take this infinite set. You can just easily, you can take this infinite set. For example, a power n, b power n. Okay, n is greater than equal to 1. This set you can take. Now you can notice in here what will happen. A power n, b power n, and a power m, b power m, are they distinguishable? They are distinguishable by whom? And let's assume n is not equal to m. So if you have two different strings from s, then they are distinguishable by a power n, b power n. They are distinguishable by a power n, b power n. This belongs to L. This does not belong to L. So I can say this set will work, and that is the reason I can say this is a this language is non-regular. Okay, so this is the analysis of this language. Did you understand the analysis of this language? Let's see the next question. WW bar. First of all, let me define what is W bar. Let me define this. Okay, let me define this W bar. Like, what is the complement of string? We know complement of set, but how to define W bar? How to define W bar? Can you tell me? What do you think? How to define W bar? We know complement of set we know, but how to define complement of a string? This is only possible when you have 0, 1. Okay, remember, this is only possible. How to define W bar? This is only possible when your binary alphabet. If your alphabet is binary, how to define W bar? First of all, this is how we define. Just flip every bit. Okay, just flip every bit. Flip every bit. Flip every symbol. So for example, if your W is 0, 1, 0, 1, 1, 1, then what will be W bar? W bar will be 1, 0, 1, 0, 0, 0. Okay, like this. If your W is A, B, B, A, A, B, then your W bar will be what? That will be B, A, A, B, B, A. Yes or no? Is this clear? So this actually W bar you can only define, and this will be defined in the exam. Don't worry about it. In the exam, they will give you the definition. This is not a standard thing. This is not a standard. So you can notice they will give you the definition. So W bar is defined only when sigma is binary. Only sigma is binary. Okay, then you can define this W bar. Now this is your language, WW bar. We have seen the language WW. Now the language is WW bar. Is there any difference? Is there any difference? Okay, the language now the language is WW bar. W bar means first half. Can I say first half must be equal to W bar? Yes or no? Or can I say, okay, this is the idea. Basically, what type of strings you have here? Look at this A, B whole star. Look at this W. So what type of strings you have? This type of strings you have. Okay, the first half. If first half is A, B, A, B, B, then the second half must be what? Tell me what should be the second half? If this is the first half, then what should be the second half? The second half should be B, A. This should be the second half. Okay, this would be the second half. Now you notice one more thing, that can you notice this is actually basically we are matching. Okay, this is also we need to remember this and we need to match with this. Correct or not? We need to remember this and we need to match. Like A should, okay, if this is A, this should be B. If this is B, this should be A. If this is A, this should be B. Okay, so like this. So we need to remember and we need to match. So is this same as WW? Is this language same as WW? Exactly same, right? This is exactly same. The language is changed, but it is as hard as WW. Equal hard to WW. I can say equally harder as WW. Both are equally hard, correct or not? Okay, both are equally hard. Yes or no? Both are equally hard. So you can notice here, this for this language, can you give me the distinguishing set? For this language, can you give me distinguishing set? WW bar. Give me the distinguishing set. Again, if there is no two strings are equivalent. Yes or no? Again, you notice that here no two strings are equivalent. No two strings will be equivalent. For example, these two strings, are they equivalent? These two strings, these are not equivalent and they are distinguishable by B. They are distinguishable by B. Okay, what about these two strings? A power 10, A power 20. What about these two strings? They are distinguishable by whom? These two strings, they are distinguishable by whom? They are distinguishable by B power 10. They are distinguishable by B power 10. Okay, so they are distinguishable by B power 10. This will belong to L. This will not belong to L. So they are distinguishable by B power 10. So like this. So quite simple this is. Yes or no? And what about like these two? I can say A power 10, B power 10, B power 10, A power 10. They are distinguishable by whom? By whom they are distinguishable? Okay, so again you can notice this will be B power 10, A power 10. Okay, so you can notice this will belong to L. B power 10, A power 10. This will not belong to L. So like this you can check. Quite simple. So this language is also non-regular. Very simple. Okay, like this you can create the set. What is the next language? The next language is this. Next language we have seen this in the last class. We have seen this. The next language. This language we have also seen. Okay, we have also seen last class. And the last is the language of palindrome. This we will see after some time. Okay, so far did you understand all the concepts? Please tell me. Do you have any doubt? Is there any doubt, anyone? Proving a language is non-regular is very easy now. I hope. This is very easy task. And this is much easier than pumping lemma. Can you notice? This Myhill-Nerode theorem, this is much easier than pumping lemma. Very easy. Do you need to take copy pen? You don't need to take copy pen, right? Okay, I hope. Like, see, this language, let's prove that this is non-regular. Prove non-regular. Prove it is non-regular. Let's assume W belongs to A, B whole star. Means W belongs to A, B, B, C whole star. A, B, C whole star. So W is a string on A, B, C. And this, what this language is saying, the language is saying that W has exactly one C. And that too as the middle symbol. Okay, W has exactly one C. And that too basically in the middle. So W is this type of string. In the middle you have C. And here you have A, B something. Here you have something called a string of A, B. Here you have anything. and here you have anything. So in this language, what we have to find out? See, do we have to remember this? Please tell me, do you have to remember this? Do you have to remember this? Do you have to remember this? Oh, yes, you need to remember how many symbols are there. You don't need to remember the string. You don't need to remember the string, but you need to remember the length, because this must be the middle. Because this must be the middle. Yes or no? This must be the middle. So what a finite automata has to do? Tell me what a finite automata has to do. At any point of time, before this C, let's assume this C has not come. Let's assume this C has not come. Okay, let's assume this C has not come. Then at this point of time, this length we have to remember. This length we need to remember. Exact length, can I say? Not even comma, okay, not parity, not even or odd. This is exact length we need to remember. Yes or no? We need to remember this exact length. I hope this point is clear. So before this C comes, this exact length we need to remember. Before this C comes, this exact length we need to remember. So how many possibilities? Tell me. How many possibilities? This exact length we have to remember. We definitely need to remember this. So that is your infinite possibilities. Again, you have infinite possibilities. What these infinite possibilities can be? For example, here the infinite possibilities can be, I can say a power 2, a power 3, a power 4. These are the infinite possibilities. Correct? These are the infinite possibilities. Here you can have a power 3, here you can have a power 4, here you can have a power 10, a power 100, a power trillion, a power billion. Okay, you can have anything. So you can notice we have infinite possibilities, right? Okay, so this language is non-regular. Okay, but now one thing you can notice. Okay, one interesting thing I want to tell you. After this Myhill-Nerode theorem, this informal method will seem more complicated than Myhill-Nerode theorem. This informal method, it will seem, I can say, worse than the Myhill-Nerode theorem itself, because you can notice you can very easily prove using the formal method. Just tell me the formal method. Give me a distinguishing set. Give me infinite distinguishing set. Give me infinite distinguishing set. Remember these infinite possibilities, these are the infinite distinguishing set. Correct or not? Did you make this observation? These infinite possibilities is the infinite distinguishing set. Infinite distinguishing set. Okay, did you make this observation? Tell me, did you make this observation? This is infinite distinguishing set. Can I take any set? Like someone is saying, can I take any set? Can I take this set? For example, can I take this set? A power n, C power 2, B power n. Can I take this set? N is greater than equal to 1. Can I take this set? No. In this set, this is actually pairwise equivalent. Yes or no? This is infinite set of pairwise equivalent. Infinite set of pairwise equivalent. These are actually pairwise equivalent. Yes or no? These are pairwise equivalent. Because remember, okay, whatever extension you put, they will not be in the language, because in the language you have only one C. So in the language you have only one C. So I can say they are actually pairwise equivalent. Whatever extension you put, you can put anything and they will not belong to L. All of them, they will not belong to L. So this will not work. Give me a set A power n, this will work. Take this set A power n. Now tell me here, this A power n. Now you can take A power m, A power n. You take two different elements where m is not equal to n. Now who will distinguish them? Tell me. Who will distinguish them? This does not belong to L, this belongs to L. Who will distinguish them? Tell me who is going to distinguish them? C A power n. Can I say C A power n will distinguish them? Yes, C B power n will also distinguish them. I can say C B power n. C B power n. Okay, A power n is also fine. So can you notice that this will not belong to L, this will belong to L. So that is the reason I can say this is your infinite distinguishing set. So you can notice that these infinite possibilities, these are basically the infinite distinguishing set. So whenever someone tells you, okay, if someone is telling you, see, DFA has to keep track of infinite possibilities, DFA has to remember infinite things, then basically what they are telling you, they don't know they are telling you, but basically what they are telling you infinite distinguishing set. They are giving you infinite distinguishing set, but they don't know this. Many people don't know this. Many people will say this line they will speak, this line, that DFA cannot remember infinite things. This line they will remember, this line they will speak, but they don't know what is behind this line. Okay, in the I can say behind this line, what is happening, what is the story, that they don't know. So this is the story we have seen. Okay, this is your set of all even length palindromes, WWR. So what type of strings you have here? In this, what type of strings you have? This type of strings. Like, okay, WWR. Remember, the length of W is equal to always length of WR. Yes or no? This you already know. Length of W is always equal to length of WR. Okay. So this always happens for all W. So you can notice here. Here you can notice this is WWR and the length is same. So the length of this and length of this is same. So I can say the first half is W and the second half is WR. Okay, this is your first half. This is your first half. This is your second half. This is your first half. This is your second half. So here, if your first half is this, then tell me what will be the second half. If your first half is this, what will be the second half? The second half will be BA. This will be the second half. Okay. So very simple. This is your language. First, you understand the language. So can I say every string will be even length? In this, can I say every string will be even length? Yes. Okay. The length will be, that length will be even. Okay. So this is your set of even length palindromes. Now, can you prove that this is a non-regular? What is the informal method? What is the informal method? Tell me. For this WWR, the informal method, what is that? That is very simple. First of all, you can't even find middle. DFA can't even find middle. You can't even find middle. This middle, FA cannot find middle. FA cannot find this middle also. First of all, you can't even find the middle. Okay. All the other things are different. But first of all, you can't even find the middle. And by chance, if you find the middle, by chance, if you find the middle, actually you can't find the middle, but let's assume by chance, if you find the middle, then you have to remember this. You have to remember this exact string. This exact string, you have to remember this W. Okay, you have to remember this W so that you can match with W reverse, so that you can match with here. So this W you have to remember. Okay, and if you have to remember this W, so there are infinite possibilities. This W can be anything. There are infinite possibilities. Okay, we have infinite possibilities. So this W can be anything. Okay, for example, this W can be anything. This can be A square, A cube, and so on. This W can be anything. So you can notice. For this language, can you give me infinite distinguishing set? Give me infinite distinguishing set. Infinite distinguishing set, can you give me? This set will work. A power n is greater than equal to 1. This set will work. In this set, you take any two strings. Any two strings you take, m is not equal to n. If you take any two strings, then what will happen? If you take any two strings, then what will happen? Give me that this belongs to L, this does not belong to L. Give me something. Give me something such that this will belong to L, this will not belong to L. Alap, you cannot give me B a power n. Will this work? Will this work? B a power n. Will this work? B a power n. Will this work? No, now this does not belong to L because this is odd length. First of all, this is odd length. First of all, this is odd length. Okay, so this will not work. You cannot give me B a power n. Give me something else. So this will not work. Okay, so B power n, this extension will not work. Remember, extension B a power n doesn't work. So which extension will work? Give me some extension. Yes, very easily. You can give me some extension. Okay, one more thing. Can I take a power n simply? Can I take simply a power n? Can I take simply a power n? Can I take simply a power n? Simply can I take a power n? Now also this will not work. Now also this is wrong. This is also wrong. What is the reason? For example, a power 4. Okay, and for example, a power 10. For example, a power 4, a power 10. Now if you take a power 4, this is also a power 4, a power 4, and this is also a power 7, a power 7. So both belong to L. So both belong to L. Yes or no? So both of them will belong to L. So you cannot take this. So give me something. Give me something concrete. Okay, let me give you b power n, b power n, b power n, a power n. Can I do this? Can I do this? B power n, b power n, a power n. Now can I do this? That's it. That's it. Now you can notice. So now you can notice this will belong to L and this will not belong to L. Now you can check. Now you can check this will belong to L, this will not belong to L. Okay, very simple. So this is the idea. I hope all these points are clear. So this language is also non-regular. What about this language? This language is set of all palindromes. Is this same as the previous language? Is this language same as previous language? In this language we have strings. In this language we have strings whose reverse is same as itself. So in this language actually we have all the strings. So this type of strings will also have. This also we have. Every string whose reverse, okay, every string whose reverse is same as itself. Every string whose reverse is same as itself, we have. So we have odd palindromes and even palindromes. Basically in this we have, in this contains, I can say this PAL. This is actually, I can say, odd palindromes. Okay, this actually odd palindrome union even palindrome. Okay, so this is the union of both of them. Is this regular? Is this language regular? Is this language regular? No, again the language is non-regular. Because again what you need to do, whether it is odd palindrome or even palindrome, what you need to do? What is the first thing you need to do? Odd palindrome or even palindrome, what is the first thing you need to do? This middle, at least you need to find. At least you need to find the middle. Can't find middle. Can't find middle, right? Okay, FA can't find middle. This is your FA. It can't find middle. And by chance, if you can find middle, by chance, if you can find middle, by chance, if you can find middle, then what is the problem? Then what is the problem? We have to remember this. Then what is the problem? We have to remember this. This exact string, this string W, this exact string W, we have to remember. Remember W. And because you have to remember W, so what else? Because you have to remember W, so there are infinite possibilities. Okay, there are infinite possibilities. This W can be anything, right? There are infinite possibilities. Because this W can be anything. This W can be anything. This W can be, for example, this W can be A, this can be A square, this can be A cube, this can be anything. Okay, or maybe I can also, okay, let's back to back we are taking A. So let me not misuse A. Let me take this type of W can be this, right? There are infinite possibilities, correct? W can be this. So you can notice there are infinite possibilities. Now you tell me, for this language PAL, for this language PL, give me infinite distinguishable set. Give me infinite distinguishable set for this. So your language is PL. So you can give this set. What you can say? You can say that your set, for example, this 0 power n, 1 power n. Okay. Here you have, okay, AB. So this A power n, B power n, A power n, B power n, where n is greater than equal to 1. This you can give. And you can notice they are pairwise distinguishable. If you take, if n is not equal to m, you can see they are pairwise distinguishable. Pairwise distinguishable. For example, A power n, B power n, and this is A power m, B power m. Then tell me, who will distinguish them? Who will distinguish them? Tell me, who will distinguish them? I can say, for example, I can say very simple, a power n, b power, b power n, a power n. This b power n, a power n will distinguish them. Okay, this will distinguish them. So very simple. Now all these points are very simple. Now let's see this question. M is not equal to n. Is this language regular? This language, look at this language, 0 power m, 1 power n, where m is not equal to n. Why this is non-regular? So this language is 0 power n. This language is like this. You have okay, means number of 0. This must not be equal to number of ones. Okay, this 0 power n, this m should not be equal to n. So tell me, what DFA has to do? What DFA has to do? Should we remember this exact number? Okay, can parity will work? Okay, like if we only remember even comma odd, will that be fine? If we remember even comma odd, that will be fine or not? No, that will not be fine. We need to remember this exact number. This exact number we need to remember. We need to remember this exact number. Okay, and because we need to remember, so there are infinite possibilities. You already know. Okay, so there are infinite possibilities. What are those infinite possibilities? Like I can say 0, 0 power 2, 0 power 3, 0 power 4. These are the infinite possibilities. So that's it. We need to remember infinite possibilities. Now you give me the infinite distinguishing set. Infinite distinguishing set. So this, I can say this 0 power n, where n is greater than or equal to 1. Can you notice that this set will work? This set will work. If you have n is not equal to m, then you can notice. Let's assume, okay, let's assume you have two strings. Let me give you two strings. Let me give you p is not equal to q. Then you can notice this 0 power p, 0 power q. Which will distinguish them? Tell me, which is going to distinguish them? Which is going to distinguish them? So I can say 1 power p will distinguish them. 1 power p will distinguish them. This will belong to L. This will not belong to L. So 1 power p will distinguish them. So this is your infinite distinguishable set. Okay. So I hope all these points are clear. Now, similarly, you have here in this language, what is the infinite distinguishing set? In this language, what is the infinite distinguishing set? This language itself, can you notice? Infinite distinguishing set. This language itself will work. L1 itself. This L1 itself will work. Any two prime number you take, any two prime number you take, any two prime number you take, can I distinguish them? Any two prime number. Okay, for example, if I take any two prime number, 0 power 3, 0 power 5, can you distinguish them? Who will distinguish them? Tell me, who is going to distinguish them? 0 power 2 will not distinguish them. 0 power 4, yes, very good. 0 power 4 will distinguish them. Very good. 0 power 4 will distinguish them. So any two prime number, you can take your choice. You can take any two prime number. For example, 0 power 11 and 0 power 7. Who will distinguish them? Who will distinguish them? 0 power 4 will distinguish. 0 power 4 will distinguish. So you can notice that any two prime number you take, they are distinguishable. Yes or no? Any two prime number you take, they are distinguishable. So this set will work. This set itself will work. Correct or not? This set itself will work. I hope this point is clear. Now this is very easy, right? Many students, they by heart this, but this is actually very easy. Okay, this is extremely easy, right? Whatever two prime number you take, whatever two prime number you take, you can find some extension you can find which will distinguish them. Okay, so this is the idea. So I hope all these points are clear. Okay, so let's take a break and we will study for 50 more minutes. Exactly at 7:30 I will leave you. Okay, then you can watch India versus Pakistan. Okay, that match you can watch. So please tell me, did you understand all the concepts? Like, are you comfortable with all the concepts that we have seen? Proving a language is non-regular. Very easy, right? I hope you are finding it very easy. Now, if anyone asks you on GATEOverflow website, in GATE exam, in interview, okay, in Telegram group, your friends from other coachings, whatever is there, whatever question comes in front of you, whatever question comes in front of you, then what you will do? For regular, non-regular, whatever question comes in front of you, just apply this Myhill-Nerode theorem. If anyone tell you, prove that this is non-regular, then don't say one comparison, two comparison, matching, not matching. Don't say these things. Just directly say, okay, infinite, this is, just directly give them infinite distinguishing set. Just directly say a power n, that is infinite distinguishing set. They will stop talking to you. They will say you are mad. Like, what are you saying? Okay, what is this infinite distinguishing set? Because actually, this is reality that many students, they don't understand this Myhill-Nerode theorem. They just by heart one, because there are two questions on Myhill-Nerode theorem. There are directly using the word Myhill-Nerode. Using this word Myhill-Nerode, there are two questions. So those students, they only understand those two questions. Basically, they only by heart the answer of those two questions. They will not understand what is Myhill-Nerode theorem, what is this distinguishable strings, what are equivalent strings, what is infinite distinguishing set, okay, how to prove a language is regular, how to prove a language is non-regular. So all these things you should understand. This is what I'm saying, okay? Because once you understand this Myhill-Nerode theorem, this regular language, non-regular language, this concept will become extremely easy for you, extremely easy, okay? So now you have everything. I taught you pumping lemma, okay? So we have already seen pumping lemma, many questions, many examples, okay? A lot of things in pumping lemma we have seen, all the variations, okay? We have seen Myhill-Nerode theorem. After the break, I will only tell you the statement of Myhill-Nerode theorem. Only that we will see, okay? So only for 1 hour we will study, okay? So, okay, thank you. Arnab is saying, for these reasons, India will know about Go classes. Yes. So Arnab, share with your friends, they will know, okay? So for you, with your friends, GATE aspirants, you can share, okay? Okay, thank you everyone. See you in 5 minutes or 10 minutes. Take 10 minutes, okay? After 10 minutes, we will resume. I will create a new session. Yes, new session I will create after 10 minutes. Exactly 10 minutes. Thank you.